Have you ever wondered how we can actually see what's happening inside an electrical circuit? That's where the multimeter comes in. It's the single most important diagnostic tool an irrigation technician can carry. In this section, we'll explore how to safely use a multimeter to measure voltage, resistance, and current, interpret readings, and apply those measurements to real-world troubleshooting. I'm Dr. DeBusk, and by the end of this lesson, you'll understand how to use a multimeter confidently to keep irrigation systems running safely, efficiently, and reliably. Whenever we work with an electrical component in an irrigation system, safety is the top priority. Every technician must be properly trained and follow all OSHA, state, and local codes, especially when working with live voltage. The goal is always to protect both people and property. The most important testing tool an irrigation technician can own is the multimeter. Ironically, it's also one of the most misunderstood tools in the field, and often the least used. Without a multimeter, it's nearly impossible to pinpoint electrical problems accurately. For irrigation, we primarily use a multimeter to measure resistance, ohms, and voltage. Measuring current or amperage can be useful for experienced technicians, but isn't typically part of routine troubleshooting. Remember, measuring and troubleshooting aren't the same thing. Measuring gives you the data that reveals trends, component degradation, and the clues needed to fix problems before they can cause system failure. To use a multimeter effectively, we first need to understand what electricity really is. Electricity works because of free electrons, those loosely held in their orbits that move when voltage pushes them through a conductor. Copper wire is a great conductor because it has plenty of free electrons, while plastic is used as insulation since it resists the flow of electrons. When those electrons start to move, we call that current, measured in amperes or amps. Think of current as water flow in a pipe. The higher the flow, the more work that has to be done, whether it's turning on a light or opening a valve. When we think of current, it's easy to picture electrons racing down the wire like water through a hose. But that's not quite right. Instead, each free electron shifts position slightly, passing energy to its neighbor, like the balls of a Newton's cradle. The energy, not the individual electrons, move through the wire. Current only flows when there's a complete circuit, a path for the electrons to travel. When a system is unplugged or a circuit is open, electricity isn't leaking out, it's simply potential energy waiting for a path. Current is what actually does the electrical work. For example, two 0.5 amp solenoids require 1 amp total. Just like multiple sprinklers increase total water flow through a pipe. There are two main types of current: alternating current, AC, and direct current, DC. AC is what powers most irrigation equipment: controllers, solenoids, and pumps. It alternates between positive and negative, which is why it doesn't matter which probe you place where when testing with the multimeter. DC, on the other hand, flows in one direction and is used in systems with batteries or decoder modules. Here, polarity matters. The red lead must connect to positive and the black to negative. Voltage is the force that pushes electrons to move, just like pressure pushes water through a pipe. We measure it in VAC for alternating current and VDC for direct current. Resistance is what slows down the flow of electrons, the electrical version of friction in a pipe. It's measured in ohms, symbolized by the Greek letter omega, which looks like an upside-down horseshoe. Resistance increases with smaller, longer, or hotter wires and decreases with larger, shorter, or cooler ones. That's why irrigation wiring needs to be appropriately sized and protected. Let's look again at the solenoid example needing 0.5 amps to open. That means it takes 3 quintillion 125 quadrillion electrons per second for the solenoid to do its work. If any of the 4 things affecting resistance makes the resistance higher and the solenoid only gets 2 quintillion electrons per second, the valve does not open. The relationship between volts, amps, and ohms is defined by Ohm's law. V equals I times R. So voltage equals current times resistance. When current, amps, increases, voltage tends to drop. This is similar to when larger nozzles are installed. It increases the demand for flow in the pipe, resulting in a lower pressure at the sprinkler head. When resistance or ohms decreases, the amps increases, and as ohms go down, the voltage does too. Understanding this relationship helps you interpret your multimeter readings accurately and diagnose electrical issues quickly. Multimeters come in two styles, analog and digital. Analog meters use a needle and scale, which can make readings tricky, especially in the field. Digital multimeters, on the other hand, display values clearly on a screen and are far easier for irrigation troubleshooting. The good news, you don't need an expensive model. A reliable digital multimeter in the $20 to $30 range will have everything you need. Spending more won't make your readings more accurate, but cheaper models might not hold up under outdoor conditions. For irrigation work, the key functions are voltage and resistance, ohms. Some models include battery test settings, but you can use the DC voltage setting for that too. Meters can be auto-ranging or manual. Auto-ranging meters automatically adjust the range for what you're testing, which makes them easier to use. Just remember to watch for small symbols like M or K on the screen that modify the displayed value. Beyond the basic multimeter, there are a few features that make troubleshooting easier and safer. If you're diagnosing pumps or have been trained to use amperage readings effectively, a multimeter with a clamp meter is a must. It allows you to measure current flow safely without disconnecting wires. For more advanced systems like 2-wire decoder setups, a milliamp meter may be required. These are specialized tools for precise low current measurements. No matter what meter you use, always invest in good accessories. Alligator clips are invaluable. They let you clip onto terminals so your hands stay free, reducing the risk for short circuits. Use durable leads made for outdoor work, and keep spare fuses and batteries in your kit so your meter is always ready when you are. Knowing whether to test with the power on or off is critical, not just for accuracy, but for your safety and the health of your meter. When your meter is set to amperage, A, it actually lets all the current pass through itself, so the power must be on. When measuring voltage, V, the meter lets some current flow through. It's also on. But when measuring resistance, ohms, the meter generates its own small current, so the power must be off. Remember the rule of thumb. Amps equals on, volts equals on, ohms equals off. Mixing that up can blow a fuse in your meter, or worse, cause serious damage. Lead placement is another key factor in getting accurate readings and staying safe. In standard irrigation systems, valve circuits run on about 24 volts AC, which has no polarity. That means it doesn't matter which lead, red or black, you put on which wire. However, when you're working on battery-operated controllers or DC decoder systems, polarity matters. Always place the red lead on positive and the black lead on negative terminals or wires. And here's the safety part. Never hold both bare wires with your fingers when measuring voltage. Even 24 volts can give you a nasty shock under the right conditions. Instead, hold the insulated portion of the wire, or better yet, use meter clips for a stable hands-free connection. Even when your settings are correct, you can still get unreliable readings if the lead placement isn't right. When testing at a controller terminal, maximize the surface contact by placing the side of the lead against the screw head, not just the tip in the slot. Minimal contact can cause your readings to flicker or jump. If your readings still fluctuate, your meter might need to be zeroed out. To do this, touch the red and black leads together until the display reads 0. It's a simple way to calibrate your meter, especially with analog or inexpensive digital models. Most technicians make it a habit to zero their multimeter before every measurement. It takes 2 seconds and saves you from chasing false readings. Before you start taking any measurements, know what you're testing and why. Every accurate electrical diagnosis begins by establishing a baseline, a benchmark to compare against future readings. In irrigation troubleshooting, we measure volts to check if power is reaching where it should, controllers, transformers, and sensors. We measure ohms to check the resistance in valve circuits, including solenoids and splices. We measure amps only in advanced cases like diagnosing high power issues or motor loads. And always keep in mind, collecting random readings without purpose doesn't help. It confuses the picture and wastes time. To measure voltage correctly, make sure the power is on for the circuit being tested. When testing controllers, 24-volt circuits, or rain sensors, set your multimeter to VAC. You'll see this marked as a V squiggle line, VAC, ACV, or a capital V with a squiggly line. Most irrigation testing is done at 200 volts AC. That's the ideal range for 99% of systems. For battery-operated devices or DC solenoids, use the VDC, DCV, or V equals setting, shown as a capital V with a straight and dashed line. A good tip is to mark your multimeter dial with a permanent marker next to the 200V squiggle, so you can find it instantly in the field. Start by measuring voltage at the controller terminal strip. This confirms that each station and output is getting proper power. Attach your black lead to the common terminal and your red lead to the station, pump, or sensor terminal being tested. Keep an eye on your display. If you see an MV, millivolt icon, the reading must be divided by 1000. Next, measure voltage at the transformer output. Connect the leads to the two transformer terminals, not the ground wire, which is the yellow striped green wire. Record both readings for future comparison. Consistency across stations indicates healthy electrical flow. Large differences suggest potential wiring or solenoid issues. For transformer input, measure power at the wall receptacle or junction box. Push both meter leads into the plug slots. This ensures proper contact even in tamper-resistant outlets. To check valve voltage, begin with the power off unless you can get good wire contact with wire nuts on, like shown in the photo. If you can, expose the solenoid wires, clean corrosion, and connect your meter leads. Then turn the power back on to measure live voltage. Voltage readings here verify whether the controller is delivering full power to the valve. If the voltage drops significantly, it can signal a weak transformer, poor splice, or failing solenoid. To measure battery voltage, set your meter to the correct DC setting, either the battery test position or the 20 VDC for most meters. Place your red lead on the positive terminal and black lead on the negative terminal. Typical thresholds. If a 1.5 volt battery reads below 1.3 volts, replace it. If a 9 volt battery reads below 6 volts, replace it. Even a small voltage drop can affect the operation of battery-powered controllers or latching solenoids, so routine testing helps prevent system failure. When testing resistance, always remember, power off first. Measuring resistance, shown as ohms, or the omega symbol, tells us how much opposition there is to electrical flow. In irrigation, resistance testing helps verify the condition of the valve circuit, including the wires, splices, and solenoid. Most healthy irrigation circuits will read between 20 and 60 ohms. If you see a value outside that range, disconnect the common and station wires from the terminal strip and retest. This ensures you're not accidentally reading through the controller's internal circuitry. Your meter might also show kiloohms or mega ohms. Those simply mean multiply the number by 1,000 or 1 million respectively. To check the health of a full valve circuit, measure resistance directly at the controller. Start with the power off and set your meter to the ohm setting, or 200 ohms if your meter isn't auto-ranging. Attach your black lead to the common terminal, C, and your red lead to the station or pump terminal you're testing. If your display shows a kiloohms or mega ohms symbol, remember to multiply your number appropriately. This catches a lot of technicians off guard. If your reading is below 20 ohms or above 60 ohms, disconnect the common and station wires and retest to rule out the controller itself. A great tip: take your meter to a local irrigation supply store and measure new solenoids. This gives you a reference list of normal resistance readings to compare during troubleshooting. When you need to isolate the solenoid itself, the process is similar but requires exposing the wires. Start by turning the power off, cutting the old splice, and restripping the wire ends. Clean off any corrosion using plumber's cloth or the edge of your wire strippers. Connect the red lead to one solenoid wire and the black lead to the other. If your display shows kiloohms or megaohms, adjust the reading by multiplying by 1,000 or 1,000,000 to get the true resistance. Record your reading and then reconnect the wires using a waterproof connector. As with all resistance testing, remember to use clips whenever possible to avoid hand interference or inaccurate results. Let's wrap up with the big picture. A multimeter is one of the most powerful tools in irrigation maintenance, but it's only effective when used with purpose, precision, and safety. Always know what you're measuring and why. Use volts to verify power, ohms to check resistance, and amps only when you're trained and equipped for advanced diagnostics. Remember, power on for volts and amps, power off for ohms, and a healthy valve circuit usually reads between 20 and 60 ohms. Finally, record your measurements. Over time, these readings become your benchmark library, the data that separates guessing from skilled troubleshooting.